Okay, so this example here is actually goes with example 5 from section 12.7. Centroid, center of mass type problem. All right, but we're doing it now. You've seen center of mass type problems for a lamina in back in section 12.5. Okay, now we're going to do a center of mass or centroid problem for a solid in three-dimensional space, an object in three-dimensional space. Let me give you a moment to copy. Okay, so what's the first thing that that you think might be that we should do for this problem? That could be very helpful. I mean, how should we approach this problem? What do we have to do first? I agree, Christopher. We have to draw it. Okay. So our solid, we have to draw this solid. And the solid is bounded by a parabolic cylinder and the planes x equals z, z equals 0, and y equals 1. Now, z equals 0, when you say z equals 0, what's another way of saying z equals 0? The xy plane. That's right, Ryan. Okay, so and what's going to bound this solid on, so below, this solid is bounded below by the xy plane. What about above? The solid can't go up forever. What's stopping the solid from going up forever? You know, which of these other equations here is preventing the solid from going up forever? Good, that's right, Ryan. X equals z. Or you could think of it as z equals x. All right, that's going to be a plane, okay, that bounds this solid from going above. Okay, now the solid can go forward, right? What about the solid moving forward along the x-axis? What's stopping the solid from moving forward along the x-axis? Which of the equations is preventing that from happening? Good, Diodoth. The plane x equals 1. That's cutting the solid off. Okay. So let's go here to the solution, and here's a picture. Here's a picture. Okay. So the x equals y squared is a parabola in the x y plane, but then in three-dimensional space, it's a parabola that goes up and down forever. But the parabola stops at the plane z equals x above, and it stops at the plane, well, you know, we have the plane here, z equals 0 below. And this is what the figure looks like. Take a moment and copy the figure down. Okay, okay. So now, the mass, you know, the mass, the formula, of course, is in the textbook, but density equals mass over volume, right? Density equals mass divided by volume. Okay, one moment here. So mass is going to equal density times volume. Okay, and you know, here's the density. Now the density, they don't tell you anything regarding what you know, what the value is of the density. Okay, and actually, really, I think in the example, we need a little more. Let me just go back to the original example you copied down. I want you to add something here. We're going to say we're assuming constant density, right? We're assuming constant density given by rho. Okay. And rho is just, you know, they don't give us a number. They're just saying, you know, it's rho. Now, assuming a constant density will help us make our life a little easier. We don't need it though, but okay, so we assume constant density rho. Let's go back now to our thing here. So there's the density. This is my dV. Now, there's no question here I'm going to use Cartesian coordinates. Well, actually, you know, you learned about Cartesian coordinates and polar coordinates and spherical coordinates. And you can do triple integrals in all three of those coordinate systems. But here, Cartesian coordinates are going to work the best. So, okay, let's get our limits here now. Let's get our limits. So if I here, okay, take a, no, hold on. Hold on, class. Okay, so dz goes from a bottom surface to a top surface. I'm sorry. I want to say this the right way. So the z limits come first. Okay. All right. Well, based on the solid is bounded below by z equals 0. So, you know, that 0 there, that really means z equals 0, right? Z equals 0. And then the solid keeps going up until you reach the plane z equals x. So those are our surfaces on the top and the bottom. Okay. Now we have to worry about region D. We have to worry about, well, are there any questions so far? Let me make sure you're comfortable. All right. Well, for region D, okay, if we were to collapse this solid into the xy plane, it would trace out this parabola given by x equals y squared. All right, so if we were to draw a picture of x equals y squared, if we were to just draw a picture here, okay, here's x, here's y, and here's x equals y squared. Okay, and clearly it gets cut off at 1. Okay, so this is the, you know, region in the xy plane right here that I'm drawing over here, right? And in this case, well, I'm going to treat this region in the this region D in the xy plane. I'm going to treat it like a type 2 region. type 2. Okay, and so hold on. One moment here, class. So this is x equals y squared. And then the line segment there, okay, the line segment is x equals 1. Vertical line, x equals 1. So we're going from a function on the left, the x equals y squared, to a function on the right, x equals 1. And that's how you get these limits. And then finally, well, for, you know, in terms of my x limits, or my y limits, I should say, the y limits will go from -1 to 1. Okay, are there any questions on this? All right. Well, so I'm going to use iteration. So I'm going to, you know, single out that inner integral right here. I'm integrating with respect to z. So any other variables are held constant, and the rho, that rho density is a constant. So the antiderivative of a constant is just rho times z, and I evaluate that at x at 0. Okay, so I'm going to, are there any, well, let me let you give you a moment to copy up to here. Let me know if you have any questions. All right, are we ready to move to the next page? All right, maybe if I get a few thumbs up, I'll move to the next page. All right, Deodath is good. And Eric is good, good. And John, okay. Good, okay. So we're just going to continue doing the integration here. So when I put in, I want to mention on the previous page, when I put in x and 0 here, I'm going to get rho times x. And so that's what I got here. Okay, I'm going to integrate now with respect to x. Limits are 1 and y squared. Okay. I mean, now it's a you know, like a 12.3 or 12.4 problem, right? 12.3 problem. It's a double integral now. So, you know, you just work it through, and then you're going to get this single integral, and you work it through. And in the end, you're going to get 4 rho divided by 5. Let me know if you need me to go over any of the details here. I think it's pretty clear, but just ask if you have a question. Okay. Well, may we move to the next page if there are no questions? Okay, Nicholas is good. Deodath is good. All right. Well, let's do that. So now we want to find the centroid. We have to figure out the moments about the xy planes. And the first moment is the moment about the xc plane. And right away I say, oh, that equals 0. That equals 0. Now, why is that? Why is that? Well, the mass balances perfectly along the xc plane. I'll come back to this so you can copy it in your notes, but let's go to the picture. Let's go to the picture here. Okay, the xc plane, I mean, here's the, hold on here. Here's the x-axis right here. There it is, right, the x-axis. And the solid balances, it's of constant density. So the solid would balance perfectly about the xz plane. Okay, in other words, the weight on the right side of the xy plane and the weight on the left side of, I'm sorry, the weight on the right side of the xc plane and the weight on the left of the xc plane of the solid, you know, the mass is it's the same. So does it make sense that does this make good sense then? That first statement? I mean, we don't need to really compute anything. We can just use our intuition. How many's feeling good about that? about this statement here. Okay, Christopher's good. Diodath's good. All right, let me know if you have any questions. Okay, well then we need to figure out the other two moments about the YZ plane and the moment about the XY plane. So for the moment about the YZ plane, so you insert an X, right? You insert an X in. It's basically, well, I want to say this the right way. The moments are the same triple integrals as the moment as the triple integral is that for the mass, except you have to insert an appropriate variable. And since x represents a distance from the YZ plane, we insert an x in the here, and we compute this moment. And of course, the limits don't change. You can work it out and see that you'll get 4 rho divided by 7. Okay. And then similarly, you can compute the moment about the XY plane by, you insert a z, because z is distance from the XY plane. You insert that in the triple integral, and you just do the work, and you'll get 2 rho over 7. Let me give you a moment to copy. All right, are there any questions before we move to the next page? Okay, well now we have to figure out the centroid. So the centroid involves dividing each moment by the mass. And that's what I did. That's what we do. We take each moment about the different planes and divide by the mass, and this is going to get us the centroid, which is, or center of mass, which is 5/7, 0, and 5/14. All right, so let's go ahead here and let's think about this for a moment. Let's look at our answers here. We got, so we understand that y bar would equal 0. For x bar, I got 5/7. Okay, and I guess, hold on here. This is, I have something, 5/7 is greater, I want to say, than a half. And 5/14 is less than a half. I had ones there, but I meant halves. Okay, I meant halves. So, I mean, does this seem reasonable based on the picture? Does this seem like a reasonable answer? Well, let's look at the 5/7. So x bar equals 5/7. If I go back to the picture here, okay, if I go back to my picture, so x bar is how the object balances with respect to the, going in the x direction. Okay, no, I want to say that I didn't. Well, the x bar is the, if you think about the distance that, if you think about the YZ plane and the, well, the balance point from the YZ plane of the object, x bar is equal to 5/7. Now, this here is, say, that looks to me like to be about a half. And 5/7 is greater than a half. Why does x bar have to be greater than 1/2 based on the shape of the object? Why does x bar have to be greater than 1/2? Well, okay, good, Ryan. So the solid goes out, it goes from 0 to 1, okay, on the x-axis. But there is if you compare, okay, the volume or the density of the solid going from 0 to a half, okay, and then the density of the solid going from a half to 1, there's more density from a half to 1 as compared to 0 to a half. it's top heavy in the x direction. It's top heavy, the object. Okay, the density, the volume, I should say the volume. Ryan has it right. The volume is getting larger as you move outward from the YZ plane, and so it's that'll push the X bar part of the centroid past 1/2. And incidentally, now what about Y bar? What about Y bar here, or Z bar? Z bar is 5/14. 5/14 is less than a half, right? So if we go back to the picture here, if you think about now up and down, if you think about the XY plane, okay, and the solid goes from the XY plane, you know, from Z equals 0, and then the top part of the solid is at Z equals 1. Well, is the solid heavier below the, if you think about the halfway point here, vertically, is the solid heavier above or below that halfway point? Well, it might be kind of hard to see, but it's going to be heavier on the bottom, more volume on the bottom. Okay, so we get the 5/14. I mean, are there questions on this? Are there questions on that? Okay, then if you're good with that, let me get another example up here. Just give me one moment. I want to get it. I want to get it in the. I want to scan it and get it to you. So one moment, class. I was debating about doing this next example with you, but I think it's actually very good I do this example with you. I'm going to do an example from your textbook. It's actually exercise 33. Okay, so one moment. Okay, I'm going to upload it now. How many liked the center of mass problem? How many thought that was kind of cool? That one. I thought maybe I'd get a little more response on that. Okay, Christopher likes it. And Ryan likes it. Okay, and I realize these problems, because they're triple integrals, they do take time to do. So of course, you know, I'll recognize that when I assign homework. Okay, let's look at this problem here. Okay, so what you have here, it's in the recording. It's exercise 33 from your textbook, but here you have a solid. Okay, you have a solid drawn here. Okay, and the figure shows the region of integration, this right here. This is a triple integral, and the limits that you have here from z equals 0 to z equals 1 minus y to y equals root x to y equals 1, and then x goes from 0 to 1. That comes from just the solid. Okay, and what they want you to do is write the equivalent integral in the 5 other orders. Okay, so like for instance here, right? Okay, you have dz, switching to my stylus, dz dy dx. So what would the next natural, those are your different, those are the order of integration. dz dy dx, what would be natural to come next after dz dy dx? How about dz? Yeah, good. Good, I agree, Ryan. dz dx dy. Okay, that would be a good choice. All right. And then we could have dx, dy, dz. We could have dx, dz, dy. We could have dy, what? dy, what would the next one be? Well, dy, dz, dx. And then you could have dy, dx, dz. So they've done the dz, dy, dx for you. They want you to find these other 5 iterated integrals. All right, so let me take you through here. Well, I'm sort of the surface might be a little hard to copy, but is anybody copying it, or the solid? I'll wait a moment before I move forward. All right, well, think about what would the limits be like for dz dy, for dz dx dy, dz dx dy. Okay, what would the limits be? So let me go to the next page and show you how you want to work this, okay? So, well, let me show you one thing too, though. Hold on, before I go to the next page. Before I go to the next page here. So, how are they getting, just for the one they gave us, they're getting z equals 0, like the limit z equals 0 and z equals 1 minus y. So if we were to, draw a line segment going from the bottom to the top surface. The bottom surface is z equals 0, right? That's the xy plane. And then the top surface is z equals 1 minus y. That's the plane that is the top of the solid. All right, are there any questions on that? All right, if we're good with that, then of course what we have to do then is, you know, so like for the one they did, you know, for the one that they have where they go from, you know, for the y limits are root x to 1 and the x limits are from 0 to 1. Well, dy dx, they're treating the region in the xy plane like a type 1 region. And so if you take, and this will actually be a good thing for the recording, right? If you take your solid here and if you were to project it down into the xy plane, you would have a region that looks like this. And so if you're doing dy dx, well, dy dx is a type 1 region. So you're going from y equals the square root of x, the bottom function, to the top function y equals 1. And that's how you get these limits. And then, of course, your x limits go from x equals 0 to x equals 1. Now, on the other hand, if you want to do dx dy, then you're treating the region in the xy plane as a type 2 region. And so you're going to go then from a function on the left, which is x equals 0. Okay, this is the same region as above. Okay, but you're going from a function on the left, x equals 0, to a function on the right, x equals y squared. Okay, and then the limits go from 0 to 1. Okay, so let me give you a moment just to copy. Well, I mean, are there any questions on that? I think this example might be better if you just sort of followed along, kind of like, and just kind of ask questions if you need it. It'll be in the recording. But are there any questions before we move forward? Okay, let's go back to the picture. Now what I want to do, I want to do dx, hold on. I want to do dx, dy, dz. Okay, I want to do that next. So for dx, what I have to do is, well, now I'm going to have two sideways surfaces. Okay. A surface going from the YZ plane. Hold on now. I want to be a little bit careful here. Now, wait. Hold on, class. One moment. Yeah. Actually, yeah. A surface going from the YZ plane okay, make this surface going from the YZ plane back here out to the parabolic cylinder y equals x squared, or x equals y squared. Okay, and then if you, and then so that's going to be your limits for the x limits. You're going from x equals 0, which is the yz plane, out to x equals y squared, which is this parabolic cylinder out front that bounds the solid in front. Okay, front and back along in the x direction. That's what you're doing with dx. And then if you project this solid in, well, if we're doing dx, dy, dz, what plane do you project the solid into? If you're doing dx, dy, dz, what plane does this solid get projected into? So when you're doing like dz, dx, dy, people have no problem taking the solid and projecting it down into the xy plane. But now we're doing dx, dy, dz. So if the dA part here is dy, dz, we have to project the solid into the what plane? That's right, Ryan, the YZ plane, the YZ plane. And in fact, what would that region look like? Well, remember, along this rim here, this rim of the solid also satisfies z equals 1 minus y. Well, that's what it does satisfy. The rim satisfies y equals root x, but it also satisfies z equals 1 minus y. And so therefore, this is what your region D is going to look like. And essentially, you're treating with dy dz, you're treating region D like a type 2 region. And so you're going to then go for the y limits, you're going from a function on the left to a function on the right. Well, the function on the right is z equals 1 minus y, but you could express that as y equals 1 minus, y equals 1 minus z. And so those are your two limits. And then your z limits go from 0 to 1. Okay, take a moment to think about that. All right, and then if you did dz dy instead of dy dz, based on the way I have my axes, my y and z axes oriented, dz dy, I'd be treating the region D like a type 2 region, and so I'm going from a bottom function z equals 0 to a top function z equals 1 minus y. And then the y limits go from 0 to 1. Okay. Now I'll tell you what. I'll tell you what. Do you think you could try on your own to get I mean, what's left now to do? What's left to do is dy dz dx, and you have dy dx dz. Take a few moments and see if you can get those limits, dy dz dx and dy dx dz, and all have the figure up here for you. Let's see what you can do. Let me give you a few moments. I'm going to be curious if anybody gets the right answer, okay? All right. I think some of you will, but let's just see. All right, so let's take a look at this. So we're going to do dy dz dx. So now for the from surface to surface, okay, you got you're going in the y direction, okay? So you have a surface in the back. Okay, I want to do it right. I mean, this is the direction you're going. All right, and you have a surface in the back, which is given by y equals the square root of x. And then you have a surface in the front, which is the plane, z equals 1 minus y. Or you could think of that as y equals 1 minus z. Okay. Is that good so far? Is that good so far? Are there any questions? Okay, well then, all right. While we're at it here, let me just see here. Hold on, everybody. Hold on. Let's think about the XC plane. So if we project this solid into the XC plane, what would the region D look like? What would the region D look like? Okay, so again, just to remind you here, what we're doing is we're doing now dy dx dz. Okay, so what would the region look like? All right, well, let me go ahead and draw a x z plane, and I'm going to have to. And it turns out that the region, what it's going to look like, is going to be this. This parabola, well, it's going to look like that. It's defined by this rim here, right? This rim. It's defined by that rim. And that's what the projection of that rim is going to look like in the XZ plane. So this rim has equation z equals 1 minus the square root of x. And the reason it has that is because along that rim, both y equals the square root of x and z equals 1 minus y have to be true. So if you then, if both of them are true, then this y here would have to equal root x, and z would equal 1 minus root x, or you could think of that as x equals the quantity 1 minus z squared. Okay, that's what that would be. And so, and by the way, these points here are 0, 1. And this point here is 1, 0. And so, since you're doing dx, dz, you're treating this region like a type 2 region. And so, this would be your arrow here, or your line segment, and it would go from the vertical line x equals 0 to, come on, give me some x equals 0 to x equals 1 minus z squared. Okay, that's what it would do. And so now you get all your limits. But is this, I mean, is this helping you? I know this is not easy. This is the first time you're really, you're really learning it, right? When you're doing different orders. But are there any questions? Okay. Deodath, how are you feeling? Well, Dan, how are you feeling? All right, good. I was getting worried there. I want to make sure my students are here. All right, good. And Deodath, excellent. All right, well then class, if we go then to the last page here, okay, so I obviously don't have everything here I want, but if we do dy, dx, dz, the limits are going to go from root x to 1 minus z. And then the x limits will go from 0 to 1 minus z quantity squared. And then the z limits go from 0 to 1. I mean, this problem is, if you can do this problem, or you'll see others like it. If you can do those, you're pretty good with your triple integrals, at least as far as finding the limits. The other one, of course, the last one, which is dy dz dx. Okay, so the y limits are still going to be, I'll put them in maybe red here. This is a really cool problem. Root, what is it? Root x to 1 minus z. And then for the y, or for the z limits, we're treating that region that you just saw as a type 1 region. So we would be going from z equals 0 to z equals 1 minus the square root of x. Okay, and then we'd be going from x equals 0 to 1. Okay. Are there any questions? Any questions? Okay, let me stop the recording. Wait, hold on. One moment. How did I get the limits for the dy? Hold on here. All right, Ryan, let me go back to the solid. So, all right, this answer's okay. This answer's okay. Let me go back to the solid. So dy, you're going in this direction. You're going in the direction of the y-axis. So that means you have a surface. You have a surface on the left here that you're starting with. And then you reach surface on the right. Well, the surface on the left is y equals square root of x. That's why you have the square root of x in your bottom limit, because it's the, you're going from left to right, smaller to greater, left to right. So y equals root x is the surface on the left, and then the surface on the right would be the plane z equals 1 minus y, but that can be written as y equals 1 minus z. And that's how we got those limits for the dy. Okay, you're welcome, Ryan. You're welcome. All right, are there any other questions? Okay, I'll stop the recording.